Welcome back. We are in week 7. Continue with symbolic execution and start a specific technique for symbolic execution in this lecture. I'll recap from where we left the last lecture. We saw a summary of symbolic testing, saw it working on several examples, then ended our lecture with the disadvantages of symbolic testing. One is the path constraint becomes such that it has conditions that cannot be solved by any constraint solver, state of the art. And the underlying program could use functions whose source code is not available, so I have to figure out what to do. And the path constraint could be so large that it's not a feasible option to explore all path constraints because the program has many paths. So there are several workarounds. One is, of course, expansion of computers, as I told you, and modern SMT solvers being able to solve a lot more constraints with new decidable theories, and computers being able to process data faster. And there are several symbolic execution techniques itself that have work around symbolic execution to be able to use it to the best possible extent. One such technique that we will see is Concolic testing. So one of the first papers to propose Concolic testing was a PLDI. PLDI is a conference, 2005 paper. I will give in the list of references at the end. And they proposed a particular testing technique called DART. DART stands for Directed Automated Random Testing. We'll understand what these terms mean. And it is also a concolic testing technique. Concolic is not a full English word. It's just an acronym for concrete plus symbolic. So it does symbolic execution. Whenever symbolic execution is not possible, it does concrete or normal execution of a program like we do in software testing always. So suppose I take the same program, example 2. I hope you remember what it is. It was there a few slides ago. Let me just go back to see if I can go back to that example just to briefly show you the code. Yeah, so this was the example. So if these two if statements pass, that is if z is equal to x and x is greater than y plus 10, then you lead to an error. And along the way, there is a function call that basically computes z as 2v and proceeds. Of course, this example symbolic execution worked fine. We saw how to do it. But let's see how DART works on this example, just to understand what DART is about. So the same example, concolic execution or DART always starts with coming up with a random input. So assign random input values to all the inputs in the program. For that particular example, number 2, the inputs were x and y. So let's say we assign x as 22, y as 7. Then you execute the program on this input as if you were executing it normally with the inputs 22 and 7 for x and y respectively. You also execute the program symbolically, side by side. So because we gave this random inputs as concrete inputs, let's first see what the concrete execution, the path is taken. So it basically takes the else branch of the if statement. Then symbolic execution will generate the path constraint x naught not equal to 2y naught. Then what will happen is that whatever path constraints it generates, concolic execution works by flipping the path constraint. That is, negate the path constraint, take the reverse of the path constraint. If it took the else branch, now negate it to make it take the then branch, and vice versa. This will force the program to go on a different execution path. Now concolic execution will test the next if statement. So it will test for the path constraint x naught is 2y naught and x naught is less than or equal to y naught plus 10. This is one more path constraint. Now you negate the second path constraint in this list. First one has already been negated. Second path constraint is x naught less than or equal to y naught plus 10. Negate it to get it as x naught greater than y naught plus 10. Solve it, you'll get 30 and 15, and you know that reaches the error state. After these 3 execution, all the program paths have been explored. This is the same thing that symbolic execution did. The only extra step in this case we did was to start with a random input and see what the program path taken is. So that's what in general concolic testing does. Instead of executing the program purely symbolically to start with, always concolic testing starts by executing a program on a randomly generated set of inputs. Whatever the inputs are, it picks up that, figures out values for the inputs in a random way, and starts executing that program on that randomly generated set of inputs. As the program executes, whenever there is a decision statement, the program goes through a particular choice for that decision statement, either the true or false. So it picks up the path constraint corresponding to that choice and keeps it in an order, let's say in a stack. Now, for each path constraint that this program executes, as it is given the random input, concolic testing keeps track of the path constraints, and per path constraint, it negates it to explore the alternate path. So like this, it explores different variants of paths that you get by concretely executing the program on the random input. This way, you repeat this execution till all the paths are explored or whatever user-defined coverage criteria is met. So let's take the same kind of example. I've written it in a slightly more concise way. So it's very similar to the earlier one. So h is the function that we want to test. So h basically has these two nested if statements. And if it reaches this abort, then it means that there is an error. The first one says same, x is not equal to y. Second one calls f, which is 2 times x, as x plus 10. If these two pass, then you say abort. So if you now think of it as, it's a small program, but let's say you think of it on a slightly different scale. So there is a large program which has several different decision paths, and error is somewhere hidden deep in the program. Let's say you have to pass the first while, then there is an if which you have to fail, after which there's a function call. Inside that function call, there is a loop. Like this, some complex control structure is there which involves several decision statements. And the error statement is hidden deep inside the program. So by symbolically testing it, you collect several path constraints, and you might take a long time to reach the error, or even by giving it random inputs, you might, the probability of you reaching the error is very low. So how will I be able to systematically reach the error? That's where concolic testing comes into picture. So as I told you, reaching this particular function statement in this function h is difficult using a randomly generated input. But I use the same randomly generated input along with symbolic execution. That is, do concrete execution and symbolic execution or concolic execution. I should be able to reach the error statement in a systematic way. So I randomly generate some inputs. Let's say x is 36, x is 26, y is 34. Then I say, okay, x is not equal to y. First if statement passes. F of x is equal to x plus 10. No, second if statement fails. So I collect the predicates for which passed, which failed. Then per predicate that I collect, I negate one at a time in an orderly fashion. And that gives me alternate program paths. For example, I negate the last predicate. That will give me an alternate program path where the first if passes, the second if also passes, and that reaches the error statement. So this is what concolic testing does. So in summary, we will see Dart algorithm in more detail. In summary, the easiest way to remember symbolic testing versus concolic testing is symbolic testing always executes programs on a symbolic set of inputs, collects path constraints. The entire set of path constraints that it collects gives it to a constraint solver, and each path constraint gives rise to one test case that corresponds to a different execution path in the program. Symbolic testing may not be feasible for the reasons that we just saw at the beginning of this lecture. So we resort to a slightly different technique for concolic testing. Concolic testing generates a random input, executes the program concretely on that random input, and also symbolically simultaneously. Concrete execution drives the program through a specific program path. It collects the path constraints along those program paths for the symbolic inputs, flips the path constraints, that is, negates one at a time, each clause in the path constraint that it contains, explores alternate program paths. This is what concolic testing does. Concolic testing is what is implemented in modern day symbolic execution tools. So here I have listed some popular tools. Qt is Concolic unit testing engine for C. JQt is Concolic unit testing engine for Java. PEX is available as a Visual Studio plugin for .NET. Sage is another tool. Plenty of tools are there. I'll show you the list of tools. Proprietary, open source, several different tools are there. So now what we will move on and do, I'll switch slides, is to look at the algorithm for Concolic testing that was first proposed. Now the state of the art has several different algorithms. Within the scope of this course, we may not be able to look at all the algorithms, but let's look at the first algorithm for Concolic execution, namely Dart, Directed Automated Random Testing, that was proposed. So Dart, this is just an independent set of introductory slides. As I told you, Dart follows a combination of symbolic execution and concrete execution. So it's a Concolic testing tool. So what does it do? Dart is a fully automatic testing tool. So given a program, Dart uses three strategies to be able to automate testing of this program to explore different program paths. First, it extracts the interface of the program with the external environment. Don't worry about what we mean by static source code parsing. We don't have to know that. Basically, first, Dart figures out what the inputs to the program are. We should be able to figure out that on our own also. Then for those inputs, it comes up with random values and writes a test driver. Remember what a test driver is? We've seen that earlier. The test driver takes this randomly generated set of inputs and runs the program. As it runs the program, it collects new test inputs and path constraints. And how does it collect new test inputs? It solves the path constraints, negates the portions of path constraints that it collects to explore alternate program paths, gives it to a constraint solver, solves the path constraint, and uses them to drive the program along alternate execution paths. So these are strengths as documented by the paper that Dart has. I'll skip this. I'll take the same example. We will quickly revisit it. It's exactly the same example. So the example illustrates a problem with random testing as we just saw. It's difficult to reach the error statement. So how does Dart do it? Dart starts with a random value. Last time we saw one set. Let's say we take another set. It's the probability that this random set of values, 354 for X, 34,567 for Y, will hit the error statement. So it first passes the first if, but fails to execute the second if, so the error is not encountered. So along with the normal execution, Dart collects the predicates x0 not equal to y0 for passing the first if, and 2x0 equal to x0 plus 10 for the second if. Please note that this function f of x is called and returned as 2x0. That needs some work. These are symbolically executed. So x0 and y0 are the symbolic values for x and y respectively. So we take this, we give it to a constraint solver. Constraint solver will give me expressions that will pass the first if, fail the first if, pass the first if, and pass and fail the second if. So the three different program paths can be executed by taking and starting to run the program on one input and collecting the path constraints along the way. So as the tool executes the program on this randomly generated inputs, it assigns symbolic values to all the inputs, and it gathers knowledge about the execution path of the program on that randomly generated concrete input. The part where it gathers knowledge is through the path constraints, whether they passed or failed. That way it does a directed search. And what it does is it collects these path constraints and then flips the last path constraint that it encountered. You could even flip the first one, but you have to keep an order. Flips the last path constraint. Flipping meaning negate the last path constraint that it encountered. That will make the decision turn to the other path. If the last path constraint was true, then the flipping it will make it take the false branch, and vice versa. And it takes this, explores the neighborhood. Then it takes the next path constraint that it has. Again, it negates whatever it was. So if it was taking the true branch, it will now take the false branch, and vice versa. So this way, using one random execution to start with, side by side with symbolic execution, collecting path constraints for that random execution, keeping them in an arranged order, flipping their by adding a negation at the end will let Dart explore all the neighboring program paths that result from that path that the program took for that random input. And Dart repeats this process to explore as many program paths as possible. Note that this basic idea can also be used to overcome all the other disadvantages of symbolic execution. Suppose you had a piece of function call for which you didn't have a source code. For that point of time, you can ditch symbolic execution, come back to concrete execution, because you always execute the program side by side, concretely, symbolically. Suppose you had a large path constraint. For some reason, you know you're not going to be able to solve that path constraint. You give up on symbolic execution, go back to concrete execution. That is still better than not executing the program at all, fully symbolically. Parts of it are executed symbolically. Path constraints are collected to drive the program to alternate paths. If whenever you can't, you resort back to concrete execution and then resume symbolic execution. So this is what Dart does. I think I've shown this several times. Dart basically calculates alternate path constraints, gives them to a constraint solver. Finally, very soon hits a value that reaches the error in the program. So I'll stop here for now. In the next class, this is the one that we are trying to understand. I'll run through the same slide deck. I won't begin a new slide deck. We want to understand, suppose I ask you to design a Dart-like tool, right? How are you going to design it? How does it work? What does symbolic value x equal to x naught, y equal to y naught, or x is alpha, y is beta, what does it mean? Think a bit about it. How does it get the path constraints? How does it flip the path constraints? How does it store them? And basically, how do you know whether Dart is doing what we thought it's doing at a high level? So I'll explain this right in the next module. So this too will be continuation videos. We won't start a new module. So we'll explain the Dart algorithm in the next module. I'll stop here for now. Thank you.